Today we're going to look at making solutions. So when we're making a solution, a reminder that we talk about a solute, what we're dissolving into the solvent, the medium that it's going to go into. Together they make up the solution. So we can change the concentration simply by adding more solute. And there'd be many, many ways to tell someone how you want them to measure out that solute, teaspoons, liters, grams, moles, etc. The same with the solvent. So how someone wants to describe it, I put so many grams into so many liters, or I put so many ounces into so many cups, etc. All depends on sort of convenience, what tools you have at hand, and what you plan on doing with that information. For a chemist, they essentially have four separate ways that they typically describe the concentration of a solution: molarity, molality, mass percent, and mole fraction. We're going to look at how we calculate the first three. I'm simply mentioning the last one as you will see it at some point in the future. So let's first talk about how we would calculate molarity. Molarity, by definition, is moles of the solute per liter of the solution. So let's calculate the molarity of this example here. We have 193 grams of magnesium bromide dissolved in 500 centimeters cubed of total solution. So our solute is the magnesium bromide, so we're going to need to find the moles of the solute. All right, so we're going to have to look up the molar mass of magnesium. So that is 24.31. And we also have two bromides in the solution, so 2 times 79.90. And that's going to give us a molar mass of 184.11. So now we're going to find moles for our numerator by taking our mass, dividing by molar mass, and then our denominator, we want the total volume of the whole solution in liters. They gave us 500 centimeters cubed. That's the same as 500 milliliters, which would be 0.500 liters. We enter this into the calculator, 193 divided by 184.11. Then divide all that by 0.500, and we get 2.10, and we put a capital M for molar, and that would be read as 2.10 molar solution is the way we would read that if on a label. So what this would mean would be that there are 2.1 moles of magnesium bromide per every liter of solution. Now we have to make a special adjustment sometimes when we are dealing with ionic solutes. So a reminder, an ionic solute is either going to be in the problem somewhere it'll say ionic, or use the word electrolyte, or most commonly you're simply going to have to look at the formula and recognize that it's a cation and an anion. That is most often a metal-non-metal formula, or that it contains polyatomic ions, our other hint that it would be ionic. These are solutes that, when they're dissolved, are actually going to break into ions. So, if we're asking for the molality of one of the ions and not just the entire solute, we have to look at the subscript to make that adjustment. So in the example we just did, we found that the molarity of the solution was 2.10 molar for the entire ionic compound, the magnesium bromide. But we recognize that magnesium bromide is ionic. It's made of a metal and non-metal. So when that dissolves, I'm going to produce 1 magnesium ion and 2 bromide ions. I get that by looking at the subscripts. So for every mole of magnesium bromide, there is 1 mole of magnesium ions, and the concentration of the magnesium ion would also be 2.10 moles of the magnesium ion per liter of solution, because our subscript is telling us we have 1 mole of the magnesium ion. However, for the bromide ion, we have a subscript of 2. We have 2 moles of bromide for every entire mole of the magnesium bromide. So the concentration of the bromide ions is twice as much, because I get 2 bromines falling into solution every time I dissolve one of the magnesium bromides. So the molarity of just the bromide ions would be 4.20 molar bromide. Let's look at some more examples. I have a solution label that says 0.25 molar sodium phosphate. I recognize that it's an ionic solute because I have a metal and a cation and an anion. We have a polyatomic ion with the sodium. So I look at my subscript if I want the concentration of the whole thing. It would be exactly what's on the label, 0.25 molar. However, if we're talking about just the sodium, I see that I have a subscript of 3. That means every time I put 1 mole of sodium phosphate into the solution, it breaks apart and I get 3 moles of sodium. So the concentration of just the sodium ion would be 3 times that, or 0.75 molar. For the phosphate ion, I only get 1 of those, so its molarity would be 0.25 molar. Notice we're talking about the whole anion. It is not breaking into phosphorus and oxygen. It is a polyatomic, the PO4 3- ion. What about this one here? We have a solution that reads 2 molar C6H12O6. That's glucose. A reminder, here we would only talk about the molarity of the glucose, since it is a molecular solute. It would not break into pieces, so we would simply say we have 2 moles per liter of the glucose ion or glucose molecule. All right, so we looked at molarity. Now let's look at molality. A little bit of a tongue twister there. Illustrated with the lowercase italicized m. It's another way of expressing concentration of a solution. Again, we're going to have the numerator as moles of solute, but instead of saying per volume of the whole solution, notice it is mass of the solvent only, and that mass has to be in kilograms. Again, why would we use this? It's more convenient for some reason. And I could describe the exact same solution in either molarity or molality. Clearly, we'd have different numbers. So let's find the molality of this example solution. 199 grams of nickel 2 bromide in 500 grams of water. So molality is moles of solute per kilogram of solvent. So we need to convert our mass of nickel bromide to moles. And nickel is 58.69 from our periodic table. We have 2 bromines, 2 times 79.9. So we have a molar mass of 218.49 for our nickel bromide. So now we need to get that to moles. So we'll take our mass, the 199 grams, times 1 over the molar mass. That would give us moles in the numerator. And the denominator, we have 500 grams of water. Water is indeed our solvent. Notice for molality, we only want the solvent in the denominator, not the solution. And it needs to be in kilograms. That's the most common error, forgetting to change the mass in grams to kilograms. So this would be 0.5 kilograms. We put this into our calculator and we will get 1.82 molol, and then we would write the nickel bromide. That's the way we would write that on a label with that funny lowercase m. Okay, Now, again, just as with molarity, we could talk about the whole thing. It is 1.82 molal nickel 2 bromide. If I wanted only the nickel ions, I would look at my subscript. I have a 1. So it is also 1.82 molal nickel ions. In terms of the bromide ion, again, I would look at my subscript. I have 2, so it would be 2 times our 1.82, 2 times our 1.82, and that would give me 3.64 molal for the bromide ion. So that brings us to our last way of expressing concentration that we're going to look at, and that is mass percent. This one's the easiest. We've talked about mass percent really with a couple other things. This time we're just going to talk specifically about a solution. So it would be the mass of the solute out of the entire solution, and then to get as a percent, that would be times 100. And a reminder that the mass of the solution would be the sum of the mass of the solute plus the mass of the solvent. So let's look at an example for this. I want to point out here, when it asks what is the mass percent of each component, they are not asking you for every individual element that is part of the formula. The components mean the solute and the solvent. So we're really just being asked what's the percentage of the solution that's a nickel 2 bromide and the percentage that is water. So let's first do the nickel 2 bromide. So we want the mass of the nickel 2 bromide. So that's handed to us right in a problem. That's 199 grams. And we want the mass of the whole solution. So we want the solute, the 199, plus the 500 from the water. That's our solvent. So we put that in the calculator times 100, and we would get 28.5%. To find the mass of the water, the only thing that would be different would be the number in our numerator, because now we want the mass of the solvent over 199 grams. So notice up here I just have the formula for the solute. You want the mass percent of the solvent. You're going to put the solvent in the numerator. You may also recognize that, gee, if I only have 2 components, once I know it's 28.5% nickel 2 bromide, it'd be very easy to say, okay, the rest of it's water. I could simply say 100 minus 28.5, and we would get 71.5, same thing. So to summarize quickly, we found 3 different ways of finding and describing the concentration of a solution. Molarity, where we take moles of the solute per liter of the whole solution. Molality, where we take moles of the solute per kilogram of the solvent. And mass percent, where if we're finding the percentage of the solute, it would be mass of the solute over mass of the solute plus solvent. Or you want the percent of the solvent, it would be mass of the solvent over total mass, again, of the solute plus solvent. Right? So online you're going to find some practice problems to make sure that you're able to calculate these different concentrations.